Good morning, good afternoon, good evening, class. This is Mr. Arosena, and today we're going to continue our talk about various derivative rules with logarithmic differentiation. So in previous classes, previous lessons, I talked about how to take the derivative of an exponential function. More specifically, how to take the derivative if my function was e to the x. If I took the derivative of this had the wonderful property that it was its own derivative. Now, what if we take the derivative of the inverse of that function, ln x? What is this equal to? Well, it turns out that it can be shown that if f of x is equal to log ax, then the following is true. The derivative of log base a of x is equal to 1 over x divided times ln a, as follows. Right, the proof for this is shown in your textbook. I'm not going to go over it, but it is there. And you can probably find the proof somewhere else online as well. And you should probably find somebody showing you the proof online. But the proof is not that important. This is the important part, that derivative of a log is 1 over x times ln a. This has the neat property that if a happens to equal the number e, then this function becomes the following. D by dx of log e to the x, and we just call log e, log base e is really just ln, or ln, x, and this gives me the property of this, 1 over x times ln e. And ln e, this is just 1, so this just becomes 1 over x. So the derivative of ln x really equal to just 1 over x. Yep. And that's great, because if we get natural logarithms, then we can just take a derivative of a natural logarithm is fairly easy. If you just remember this rule in combination with chain rule, product rule, and so on. Alright, let's go through some examples of how this works. So, here's an example. Example 1. Example 1. So, find f prime if f of x is equal to, let's say, let's see, f of x is equal to, here we go, ln of sine x. Okay, if f of x is equal to ln of sine x, then we're going to recall the following. D by dx of ln x is equal to 1 over x, and then we have to remember chain rule, because we have a function within a function. So this function, the derivative of this function, f prime of x, would then be the following. We take the derivative of ln, so it'll be 1 over x. X happens to be sine x, so it'll be 1 over sine x. And then we chain on to it the derivative of sine x, which, if you recall from the trig derivative lesson, the derivative of sine x is just cos x. And this would be the derivative of ln sine x. 1 over sine x times cos x. Okay, let's go to another example. So, example 2. Example 2. So, find f prime if f of x was equal to, let's say, that was ln of x squared plus x. Okay, well, take the derivative of ln x. Derivative of ln is 1 over x. X happens to be x squared plus x. And we chain on the derivative of x squared plus x, which is just 2x plus 1. After a little bit of simplifying, this becomes 2x plus 1 all over x squared plus x. And there we go. And I guess if you really wanted to, you could factor the x out of the denominator, so you get 2x plus 1 over x plus 1, but you don't really have to. There you go. So, that's how we take the derivative of ln x. And how we can combine it with chain rule and product rule to get other derivatives if you have functions inside. Alright, one more example and I'll talk about logarithmic differentiation. So, example 3. F prime is equal to what if f is equal to, let's say f of x. If f of x is equal to, let's say, the square root of ln x squared. Well, recall that we can rewrite the square root as ln of x squared, and this whole thing is the power of 1/2. Now, using log rules, we can simplify this to be 1/2 times ln of x squared. Because again, logarithm rules say that I can bring this out here. Okay, so now we take the derivative of this, d by dx of this function, which will give us the following. We will get, this is a constant multiplier, so constant multiplier comes out and stays out. Derivative of ln x is just 1 over x, it's x squared. Chain on to it the derivative of x squared, which is 2x. After some simplification, we get the following. I'll say f prime is equal to that. F prime of x is equal to, the 2's cancel out, this x cancel out, that x cancel out, we get 1 over x. There we go. So, you can see here, you can use logarithm rules to simplify your logarithmic equation and then take the derivative of it. And it actually ends up being a little easier to work with. Okay. And I suppose you could use power rule and chain on the derivatives and continue that way, but why do that if you don't have to? Okay. And this actually brings up what logarithmic differentiation is. Logarithmic differentiation is basically use logarithm rules to simplify an equation and then take the derivative of it. So I'll repeat that again. Logarithmic differentiation is using logarithms to simplify an equation, and then after we simplify it using logarithm rules, we take the derivative. So let's take, for example, let's say I have a function y equals x to the power of 3/4 times the square root of x squared plus 1, all divided by, let's say, some ridiculous number like 4x plus 5 to the 4th. Something like that. Okay. Now, you could actually do this using a combination of product rule and chain rule and quotient rule, but it would take quite a bit of effort. Lots of algebra, I guess, not really too difficult, but it would be very time consuming and take up a lot of space. So what some people have realized, well, why don't we do the following? Let's take the logarithm of this, take the logarithm of that, and we're going to use natural logarithms because, as you saw earlier in this lesson, natural logarithms makes the derivatives fairly easy to calculate. So when you take the logarithm of this, we'll get the following. Ln y is equal to ln of this. And I'm going to simplify this using log rules. So the first one I'm going to do is I'm going to simplify. I'm not going to simplify that. I'm going to leave this. I'll write that in a different color so it's a little clearer. So I'm going to leave this portion as x to the 3/4, and I'm going to rewrite this as x squared plus 1/2. Okay, and now when you have a quotient in the logarithm, log rules say we can rewrite it to be like this: ln minus, and then whatever's in the quotient. So 4x plus 5 to the 4. Okay, that's one use of log rules. Second use, I'm going to use it on this portion here, because one of the other log rules we have says that if I have a product inside my logarithm, I can then separate it into an addition of logarithms, like that. So inside here I will have x to the 3/4, and here I will have x squared plus 1 to the 1/2, and here I have my 4x plus 5 to the 4. Okay. And lastly, again, just like in examples 3, I can take all these exponents out, and I can basically say the following. I'm going to take the 3/4 out of there. I'm going to put it in the front. I'm going to take this 1/2, and I'm going to put it in front. I'm going to take this 4, and I'm going to put it in front. Now I've got this 3-term logarithm, and I'm going to take the derivative of all these 3 terms. And I have to remember I have a ln y over here. So let's take the derivative of everything. Right. So the derivative of this, well, this is the derivative of y. So using implicit differentiation, we get the following: 1 over y times dy dx. Here we'll get 3/4, 1 over x. Here we'll get 1/2 times 1 over x squared plus 1. Chain on the derivative of x squared plus 1. Minus 4 times 1 over 4x, and then chain on the derivative of 4. After a little bit of simplification, we'll get the following: 1 over y dy dx equals 3 over 4x plus, let's see, those 2's will cancel out, so we get x over x squared plus 1 minus that 4 and that 4 cancel out, so we get 4 over x. Okay, and then last step is we want to get dy dx by itself, so I will multiply both sides by y. So let's use a different color. So y times this, y times that, and I'm going to put this down. So dy dx is equal to y times 3 over 4x plus x over x squared plus 1 minus 4 over x. There we go. And to top it all off, we already know what y is, because y is just my original function. So dy dx is really equal to y, which is my original function, which is way up here. I'm going to cheat. I'm going to just grab this. That's my original function. That's what y is equal to. So dy dx is really equal to y is this function again, times the 3 over 4x plus x over x squared plus 1 minus 4 over x. And there we go. There's the derivative of that horrendous looking rational function. And if I were to actually take the derivative using product rule and quotient rule, I would end up with the exact same answer, but it would be a lot of effort, which is not necessary because we can use logarithms to do the exact same thing, but much, much easier. Alright, that's how I take logarithmic differentiations. Okay. So we kind of follow this sort of set of steps. 1, take natural logarithm of both sides. So take the ln of each side, and then simplify using laws of logs, or laws of logarithms. Then we differentiate it implicitly, so we differentiate left side and right side, using all the rules we use, and then we just solve for dy dx, as we showed previously. Okay. Alright. Your assignment is as follows, class. And if you have any questions, come see me in class.